Hello, good morning. Welcome to this first Smart Tenants Underpin Deep Dive, or Smart Pin, to make it more brief, on AI-driven predictive maintenance for wind turbines and refineries using the Underpin Data Space. So today, this is the first collaboration effort for dissemination and communication between the Smart Tenants and Underpin projects. And I will very briefly make an introduction on this collaboration. So my name is Katia Lavin. I'm part of the Innovalia Association team in management of dissemination and communication of the Smart Tenants projects. Smart Tenants project. So today we're here to actually start on this collaboration together with Underpin project. But it's very important to take into account what the relationship between smart tenants and Underpin is. So in 2023, under the European Digital Europe project program call for data space for manufacturing deployment that was launched by the Commission, only two projects were funded. One is Smart Tenants and the other one is Underpin. You probably have heard about the Smart Tenants lately, as we have had 9 Smart Tenants deep dives, each of them focused on the 9 Smart Tenants use cases or pilots. But today we have the opportunity to learn more about the other project, which is called Underpin. Both projects' strategy for knowledge transfer and open collaborative innovation have a little bit following this strategy. Both projects have agreed to involve in these frequent smart pin deep dive online events so as to expand the European and international knowledge of manufacturing related data spaces, technologies, components, and deployments. So today, we have two speakers from Underpin that will showcase both the pilots in the Underpin project, but focused on predictive maintenance. So I'm going to very briefly introduce the event agenda. So this is the welcome and introduction slot. Then we have the presentation on AI-driven predictive maintenance for wind turbines and refineries using the Underpin data space. And then we will have a little slot for open discussion and questions and answers that will be available through the chat. If you click on the chat, you will be able to pose any questions during the entire event. So now we start with the introductions. First of all, if I'm not mistaken, Axel will be starting. So I will actually introduce Axel first. So our speaker, Axel Weissenfeld, I hope I pronounced it properly, is a scientist in the competence unit for data science and artificial intelligence at AIT, the Austrian Institute of Technology. His research spans computer vision and time series analysis, applying machine learning and deep learning techniques to solve challenges in both image based and temporal industrial data. He focuses on developing robust data driven methods for real world applications such as predictive maintenance, anomaly detection, and intelligent condition monitoring. By bridging visual and sensor based data modalities, his work aims to enable more efficient, reliable, and interpretable systems in industrial and operational environments. Before Axel joined AIT in 2012, he was working on several real time hardware platforms with a focus on intelligent video and forensic analysis for Bosch security systems. From 2003 to 2007, he also worked as a research assistant at the Institute of Information Processing at the Leibniz University of Hanover. On the other hand, we also have Apostolos Garos, which I'm going to show now because I didn't know the order of the speakers. So Apostolos Garos is an AI machine learning engineer in the Research and Development Department of Space Hellas SA, specializing in applying data science and machine learning to industrial predictive maintenance, communication networks, and cybersecurity challenges. He holds a Master of Engineering degree from the School of Electrical and Computer Engineering at the National Technical University of Athens in Greece. Prior to joining Space Hellas, Apostolos accumulated experience across startups and university-affiliated organizations, building scalable AI systems and deploying machine learning models in production environments. His background spans the full machine learning lifecycle, from model development and optimization to deployment and monitoring, with a strong focus on edge computing and operational efficiency. At Space Hellas, Apostolos contributes to the UNDERPIN project by advancing AI-driven technologies that enhance the resilience, reliability, and predictive capabilities of industrial and networked infrastructures. So, with this, thank you so much for your opportunity to join this first Smart Pin deep dive, and I leave the ground to you. Please remember to activate your microphones. Thank you.
Thank you very much, Katja, for the introduction. My name is Axel Weissenfeld, and I would like to give you a short introduction about our presentation today. So we have 4 agenda points. So first of all, my colleague, Apostolos, will give you a short introduction about the UNDERPIN project, the objectives of that, and also the use cases that we are dealing with. And after that, he will describe the refinery use case. And in the next step, I will take over, discuss the wind turbine use case, and then also how we are integrating the predictive maintenance services into the data space. So.
Thank you, Axel. Thank you, Katja. Hello, everyone. I'm Apostolos Garos, and together we will go through the introduction and the details of the first use case. So, a few words about our project. Our project is called UNDERPIN, and it's a pan-European data space for holistic asset management in critical manufacturing industries. Our consortium consists of 11 partners, and our efforts are coordinated by Motor Oil Hellas. The project started in December of 2023, and it will have a total duration of 24 months by the time of its completion. In the scope of UNDERPIN, 2 use cases are included that attempt to showcase the value that manufacturing organizations can get by participating in a data space such as UNDERPIN. Before getting into the more technical details, I think it's important that we familiarize ourselves with the context under which we are operating. We will begin by presenting some very common challenges of the manufacturing industry, starting with some more general ones. One very common is the ever-going attempt at operational efficiency that can be achieved through minimizing downtime and cutting down on operational costs. The latter, an attempt to address the latter, is by limiting the equipment lifecycle cost, which in some cases can amount for up to 20% of total capital expenditure of a company, showing us the large extent of this problem and the impact it can have for an organization. At the core of that particular cost lies something called equipment degradation that can lead through time to unexpected failures, which can result to losses of profit as well as damage to the company's reputation. Throughout the last few years, companies have tried to leverage the data they produce and collect to develop solutions that can alleviate those problems. Even though their efforts have been somewhat fruitful, there are some blockers that are limiting the value that can be gained. One of these blockers is the existence of data silos that restrict data accessibility and utilization, as well as security concerns that companies have that create a general reluctance in participating into cross-organizational sharing of information. With this situation in mind, we designed and developed UNDERPIN. The main goal of UNDERPIN is to establish a European-wide data space for manufacturing in the fields of dynamic asset management and predictive or prescriptive maintenance. Our main way of achieving that is by involving partners across the value chain to participate either as data providers or data consumers. In the case of technical and scientific partners, we give them the opportunity to provide their expertise and services to ensure data quality and also utilize data that they can find in the data space to train their own models. This high-level concept can facilitate a large variety of data exchanges. However, under the UNDERPIN project, we are focusing our efforts into exploring and showcasing the value that can be gained for an organization by receiving or providing predictive maintenance as a service. Our focus and efforts was split into two main use cases, one which revolves around refinery maintenance, and the second use case which focuses on wind farm maintenance. In the first use case, we are trying to predict failures and detect anomalies in refineries. The way to achieve that is by leveraging vendor data and operational insights with predictive models. The main motivation behind this initiative is to drive greater reliability, minimize operational disruptions, and reduce the maintenance costs of the refinery. On a similar note, in the second use case, our main goal is to address costly mechanical failures in wind turbines. The method that we follow to address that is by implementing predictive maintenance to detect issues early and optimize repair schedules. The result of that is minimizations of downtime, lower maintenance costs, and prevention of production losses. We will now shift our focus into the first use case that revolves around the refinery use case. During this deep dive, we will view things from the perspective of the data consumer, which is a company, in this case, SpaceLS, that receives data from the data space, analyzes them, creates some models, and provides predictive maintenance as a service back to the data provider. So, at the heart of our use case lies the data that we are using. We were provided with real data collected from the refinery of Motor Oil LS. We are working with temperature, pressure, vibration, and axial displacement sensor readings from 5 machine groups. The duration of the provided dataset was 7 years, spanning from 2017 all the way to 2024. The data we received were stored in CSV and HDF5 format for easier training of models. And we also utilized a service that was provided by the data space itself, which was an easy way to integrate the data with InfluxDB that made our lives easier when conducting time series analysis. A general overview of the workflow that we built goes as follows. We, as the data consumer, receive the data directly from the data space. We utilize some pre-trained machine learning models to predict sensor values for the next 24 hours. We then take the predicted values and compare them with some thresholds that are provided by the vendor. And in case some threshold violation exists, we create alerts and we propagate them back to the refinery maintenance team in order for them to handle them. At this point, we could get into more technical details and implementation details, but I think a much better utilization of our time is to go through some of the challenges that we faced them and the actions we took to overcome them. So one important challenge is that of data integration and governance. This challenge is present in every data science related project out there, and it always adds a significant level of development or communicational overhead. In our case, we were lucky, and this complexity was completely abstracted away from us and handled by the data space itself. We didn't do any integration work. We were just shown to a point where we could receive the data straight from the data space. And also, we didn't have to handle any data ownership policies since these were already handled by the data space and the contracts present in it. Another problem, more related to our particular use case, was that of data heterogeneity. I think it's normal that different sensors operating under different conditions in different machines have completely different distributions and statistical properties. In order to overcome this obstacle, we trained specific models for each particular sensor, And we also utilized a percentage-based evaluation metric to compare performance of different models across sensors. Lastly, an important problem is that of the data quality and contextual factors that exist in our use case. Specifically, because we are working with data from a refinery that is in active production, where there were some maintenance periods. We noted those periods from the data, and after verifying them with the refinery maintenance team, we removed them from our datasets along with a buffer period before and after to avoid training our models on them and potentially poisoning them. So we will not focus on the technical stuff, but we do have to close this detailed section with some details and findings. First of all, the metric we used was the weighted mean absolute percentage error. As mentioned before, the reason we used that was to evaluate and compare models across heterogeneous data and heterogeneous sensors. Our findings, first of all, our main finding was that the linear regression model had the best performance out of all of our experimentations. And the general finding is that simpler models performed significantly better than more complex ones in this task. So I will now pass the floor back to Axel to continue with the rest of the presentation and the next use case.
Thank you, Apostolos. Yeah, then I will describe the wind turbine use case. Yeah, predictive maintenance is really an important task for the wind energy sector, because I also try to motivate this here a little bit, because it faces really unique challenges. Usually these wind farms are in remote locations, and they work under harsh operational conditions. For example, as you saw in the image, they are on top of some hills or some mountains, and of course the wind can be very strong there. And then you usually don't have just a single wind turbine, but usually have a wind farm composing of multiple wind turbines. And all these factors make it quite costly, the maintenance and repairing those systems, because it's logistically quite complex to reach them. And so the maintenance cost can add up to 20 to 30% of the total power generation expenses. And on the right side, you see a wind turbine with the main components. On the left side, it starts with the blades. Then you go to the nut, you go to the gearbox, and the generator is another example on the right side there. And we are focusing on the generator. And we are trying to monitor the health condition of the generator. Let me go why we're doing that. So you can see we have wind turbine data taken from the whole wind farm. It consists of 10 wind turbines. It's an onshore wind farm, so it's on land and not in the sea. And it's a time series data, SCADA data. This is typically collected from these wind turbines. Consists of sensor data as well as status information and timestamps. And a sampling rate is usually 10 minutes. Every 10 minutes you have one sample data. And we collected data for 6 years, from 2019 to 2024. And in this period, we had 11 major component failures. 7 failures were associated with the generator, and that's why we also selected this component. The SCADA data consists of sensor data, as I mentioned before, and this can be, for example, temperature measurements, it can be pressure, it can be rotational measurements, and so on. As mentioned also before by Apostolos, pre-processing is of great importance. I'm coming to this back later, but just to give you like an idea, of course, missing values is always a challenge. So we added here also, like we found out those missing data points and we marked them. With wind turbines, you have the speciality that if the wind speed is too low, then you have like a cut in speed or cut-off speed, so the blades do not rotate if the wind speed is too low, or if it's too fast, the wind is too strong, then you also have to turn off the wind turbine. And so all those points which are where the wind speed is below 4 meters per second or above 25 meters per second are, like, for example, cut off and not considered in our calculations. Here you can also see the power curve. The green curve, for example, is a curve that is given by the wind turbine vendor. So it gives you an idea how much power you should actually generate by a given wind speed. And the 2 points, you see that you have quite data around this optimum value, and it can be too low and too high, but it gives you an idea of how the wind turbine is working. Then we design, as I said, we are looking at the generator, and we designed a model for this to predict the status of the generator. And it consists of 2 steps. We selected one parameter that's called generator bearing temperature. This is also well known in literature. It's one of the main characteristics which indicate if there is a problem with the generator. And we are trying basically to predict this temperature by a tree-based model. And we use different covariates that you can see on the right side. It's, for example, the generator. The rotations per minute are taken into consideration, also the nutshell temperature. And all these parameters are taken into consideration. And then we are forecasting basically how the generator bearing temperature should be. And we are using quantiles for that. And using the quantiles, we're basically providing or forecasting a normal operational range of values. And if it's within that, everything is fine. And if the measured temperature is out of that, then there could be an anomaly, a problem. And this is a second step that we're doing. So we're forecasting the temperature. And in the second step, then we have a sliding window mechanism to actually detect anomalies. Here you can see some results. On the left side, you see the curve. Basically, the black curve you can see here is the measured temperature. The dark green curve is what we are forecasting. And the light green is basically what I described before, the quantile, where we are predicting the normal operational range of the temperature. And if it's out there, then there could be a problem with the generator. And here, a next step, I would like to show you some results. So you can see again the same curve here. Basically, the black curve again is the measured temperature. The light green is the normal operational range as defined. And for example, you can see here when the values are outside, there could be an anomaly. And here in this violet, you can see that there are predicted anomalies 3 times. And then in this light violet, you can see actually the actual failure, which occurred around November 25th here. And the idea is, or the goal is, that we're actually predicting this failure before it occurs. And of course, in a time span that something can still be done, for example, 7 days before the generator fails, it would be nice to already know that there could be a problem with the generator, so that then something could be carried out for maintenance. And this is the next step. So of course, this kind of model has to be really included into the work of the operator of the wind turbines. And so there are different steps then that would be carried out, because if the model throws an alarm, and for example, first of all, the operator then would check again, like if there's any external reason for this. For example, there could be some maintenance work going on, and that's why the model throws an alarm. It could be that the sensor fails, and if not, then the problem would be inspected by real site engineers to identify if there's a problem or if everything is fine with the wind turbine. And the benefits are that if the generator fails, it usually takes quite a lot of time to replace it and repair it. So it's really the proactively addressing this issue really makes sense to carry out maintenance or repairments before the generator breaks. Let me come to the last step, the integration into the data space. So here you see one time the system, how it interacts. So we have connectors, which are used to actually transfer data. So let me go through this. On the left side, for example, you see the Moore. This is a company, for example, that is operating the wind turbines. On the right side, you see our premises, for example. That's just an example. And then over the connectors, the data can be exchanged very easily. As Apostolos said before, you don't have to do much. Right now, the min.io buckets are an opportunity to exchange the data. It could be also using InfluxDB. And so the data is then uploaded. And as soon as a contract is signed between AIT and Moore, the data can be exchanged and AIT can access the data and then carry out predictive maintenance. And the results are automatically stored in an InfluxDB, which then can be either displayed using a dashboard that has been developed, or the InfluxDB also has a built-in functionality to look into the data. Or of course, you can also query the data back to have an idea what's going on. And this brings me to the last slide, because the database features that have been developed that are still going on. So one thing is the vocabulary hub for the semantic data interoperability. So as Apostolos said, one challenge is, of course, that you quite often need a lot of data. And also for the wind turbines, for example, you saw in the 6-year span, we only had 7 component failures. And of course, it would be nice to have more data, more examples to learn from and to train the models on. And for this, of course, it's very helpful if you understand what actually each column of the tabular data set means. And for this, a metadata description would be very helpful to align the data. Second thing, of course, also finding data is challenging, especially if you have a lot of data sets. And to enrich the metadata is really of great value, and we have been working on that. Next step is also we are having an InfluxDB. This is due to the reason that we are mainly working with time series data. If you have, for example, image data, of course, the min.io bucket is totally fine. But with InfluxDB, you have a lot of advantages. For example, you can already carry out some pre-processing steps, like missing data can be included, or that you, as I said, you can set, for example, these cutoff frequencies of if the wind speed is too low or too high, that you don't consider these data points. And the last thing is we are also working, for example, on adding smart contracts for automatic checks, so that everything is really working without any human interaction, and that the data integrity and compliance rules are enforced automatically before exchanging any data. So,
So
thank you very much for listening, and we are happy for any questions.
thank you so much, Axel and Apostolos, for your very interesting presentation on the UNDERPIN data space and its application in predictive maintenance. I can see that there are already some questions. However, I will leave 1-2 minutes for other viewers to be able to actually interact with the chat and post their questions there. And then we start with the questions and answers section, okay? Very briefly. So, given that there have been a few more questions since we started with this questions and answers section, I start with the first question by Claudio. So, is predictive maintenance recommendations based on this 2017 to 2024 data, or does it also include real-time data? Feel free to answer.
Yes. So because I understand that this is targeted towards the first use case, we actually used the historical data sets from 2017 till 2024 to train our models and also evaluate them. That is because we are currently in the proof of concept and system integration phase in the project, and we're now entering the last 6 months of our duration, where we will be attempting to integrate it into the working refinery to also evaluate it on real-time data. However, to answer your question, these findings are not based on real-time data at the moment.
Okay, but this is something that actually can evolve into? That's my question.
Yes, it is planned. We have also been in close collaboration with the refinery maintenance team to make sure that our solution is aligned with their needs and the way they're operating. So it is definitely in our plans to test it in the real infrastructure.
That's great to know.
Can
Yes.
I ask then just about the wind turbine data? I mean, it's not so critical in wind turbine data because, as I said, like it's nice to have to know 1 or 2 weeks before something actually happens. So, but it's also planned. I mean, that you can update something on a daily basis, for example, the data.
Okay, so based on this historical data, then there can be actually recommendations that apply on real-time data. I understand.
Yeah, near real-time
Okay.
data, yes.
Very interesting. So there's a second question, which is how and by who are the data space costs covered?
Yeah, so this is a very rational question. Uh, However, unfortunately, I cannot give a straightforward answer at this point. This is something that that our team for another work package is handling and researching, and there are several solutions, several potential solutions that we will decide when we start having our first participants, interact with them, get their feedback, and see what suits our needs better. If you need any more information about that, please contact us, and we will be happy to redirect you to the relevant researchers on the topic.
Yes. May I add just one sentence? I think it's a really important topic. And as Apostolos said, we have a whole web package dealing with that and other colleagues focusing on this part. And I think it would be really maybe worth having our own presentation, just looking at these aspects. And would be
Yes.
very happy to that if you get in touch with us. That would be very
There is
nice.
actually one deep dive upcoming on business models in data spaces. So stay tuned and we'll have the chance to answer to this question in the future too. So the third question is, can this predictive maintenance as a service model be applied in other industries? Whoever wants to try to respond.
Yes, please go ahead.
Maybe the service that I think it may be two parts there. The one part is like we have a general service related with the data space, so predictive maintenance can be carried out using the data space as shown. So the same mechanism is also working for the first use case. So there's a general mechanism for that. The second one, the models have to be adapted usually to the specific use case, depending on what you're looking for and what your needs are.
But after all, if there is historic data from a production system, could we, let's say, integrate this type of model also with other type of data? I understand it should be possible, right?
Yes, but it still has to be trained and has to be
Of course.
optimized and adapted.
Of course. Apostolos, do you have any comments on this?
No, I'm covered by Axel. I just have to note that when changing industries, it's important that to notice that we have to retrain the models on the new data, but the whole workflow can possibly remain the same and just integrate the new model.
Okay, great. Thank you so much both for answering, and thank you, Claudio, for your questions. Let's start with the next set of questions by Marcelo Ambrosio. So, pretty significant dimensionality. Can the data be mapped to some subspace with less variables, like 100 plus variables plus other 30? One question here, maybe can this be applied in both use cases? That would be my question. And then if so, if it can be more prone for one of the use cases or the data sets from one of the use cases. Feel free to try to answer. The question is a little deep.
Okay, I could answer that since in our use case we have significant larger dimensionality, I think, than the wind turbine ones. So we tested that, and so the reason we have such high dimensionality is that we use several days of prior data to make our prediction. When working with this kind of sequential models that we tried, it is actually not, in general, not wise to remove data and perform dimensionality reduction. So we did not experiment with this kind of models. At the same time, we did not have any particular problems with performance in order to require the reduction of data for increases of performance.
Axel, any notes?
I think from a starting point, I think it's always good to have all data available first beginning, and then you can still reduce the data. And we selected the data by operational expertise. So we had operational experts who suggested which parameters could be of interest, and we selected a few of them from the 130. But the 130 parameters that we are measuring there or that we are recording are also including all the parts of a wind turbine, which is very complex.
Okay, understood. Thank you so much for both comments on this question. There is one question directly for Apostolos. So, quite surprising to see more flexible methods failing more. Is that not an indicative of overfitting? The linear model may be less able to pick nuances and therefore avoids the overtraining issue, whereas the XGBoost does pick up the extra detail that may be the only descriptive of the training set and not the overall trend. So, what do you think about this question?
Yes, so that's a great question, and I like that we get into this depth of technical questions in this event. So the answer to that is that actually our interpretation is that we tested models that not only are more complex, but also take more data into account. Particularly, we tested models that actually receive as an input all of the sensors of the same machine in order to predict each one of the sensors. The general idea behind that was that if there were some problematic sensors that more simplistic models couldn't fit, information from other sensors could assist and increase the performance for those particular ones. However, our finding was that exactly the opposite happened. The problematic sensors actually poisoned the models, if that makes sense, and made them perform worse, even on the sensors that had nominal performance with similar methods. That is our interpretation of these findings at the moment.
Axel, do you have any note on this, or should we maybe jump to the last question?
It's fine. Let's jump to the last question.
we can take it for granted then.
Yeah.
Okay, so the last question is that it was mentioned that the data space abstracted the work from you, which means it is doing its own thing. So who is the data space provider?
The data space provider is basically, I mean, the UNDERPIN project is creating this and has been developing the data space and also operating that currently. And
is it
yeah,
only any specific partner in Underpin who is doing
no,
this work, or is it a
no,
set of them?
it's a joint. It's a joint effort. It's a
Okay,
joint
okay,
effort.
good.
Make it work. But from us, I think Apostolos also meant like from a data science perspective, you're really far away from the data space, and you can really nicely just use the data in brackets with just. But of course, everybody's involved. And if you are more interested, we would be very happy to provide more information about that.
Of course. Apostolos, any note on this?
Yes, as Axel mentioned, it's a collaborative effort. As data scientists, we are giving our feedback on which features could help us. Of course, in the beginning, they were not designed or developed, but we had some ideas on features that could help us make our life and work easier. And they were at the end integrated into the data space. So, new scientific partners that provide pretty much the same service as us can have an easier time onboarding to the data space and getting value and data out of it.
Okay, then thank you so much for joining. It's already 12:45, so we are already over our time schedule, but this is because we had a lot of questions, so this is a good sign. Thank you so much for joining today, Axel and Apostolos. We will be in touch, and please, for the viewers, stay tuned and follow Underpin and Smart Tenancy in social media. Also, the Digital Factory Alliance, who is the organization that sets the PR office for Smart Tenants and is organizing these deep dives. And stay tuned in our social media, LinkedIn and X, for the next Smart Pin deep dives. And well, thank you so much for joining. Have a great day.
Thank you, everyone.
Thank you. Thank you.
Thank you. Bye.
Bye bye.